Hi everyone. So now we're going to talk about chapter 15, which again is all about how we can now take a particular variable, an explanatory variable, and use it to predict a particular response. So okay, my slides were not advancing. So again, just to kind of think about general procedures for regression. So when we talked about chapter 14, we focused mostly on how we graph a relationship between two quantitative variables and how we then can compute an index called a correlation coefficient, which can tell us something about the strength and direction of that relationship. So when you are trying to look at how two quantitative variables are related to each other, again, you would first graph that relationship, and then you would comment on the form, direction, and strength. So you would look at all of those things. Those are things that can jump out at you in a scatter plot. We want to make sure, again, that we have a linear relationship between our variables. Once we see that we have a linear relationship, we can go one step further and we can compute a correlation coefficient. And remember, the lowercase r is the symbol for that. And then if we have a moderate or strong relationship between our variables, it might make sense to go even one step further and try to predict one variable based on another. And that's where the regression line comes into play. We compute a regression equation, and that regression equation can then be used to more fully describe how the variables are related to each other and to also make some predictions. So if we know a value of x, we can use that equation to predict a value for y. So we're going to talk about how this all works, but I first just wanted to quickly point out what the regression equation looks like. This might be a little different from perhaps how you learned it earlier in your life if you took an algebra course in high school, or you studied geometry and you learned about the equation for a line. In our textbook, we have the basic format of the predicted y equals a plus bx, where y again is our response, a is the intercept in the regression equation, and in a minute we'll talk about what the intercept means and how you would interpret that. B is the slope, and x is the explanatory variable. So again, we're using a particular explanatory variable to help us try to predict a response. And sometimes you might see in some of our notation or in certain assignments, we might use this symbol to stand for the predicted y, so it's y with a little hat over it. So again, just as shorthand, we want you to know what that means. Okay, so rather than just kind of giving you some definitions about, this is what the intercept is, this is what the slope is, I wanted to talk about these terms within the context of a new example. So we'll work through a new example, and then we'll go back to our example with the eyelash length and eye width to see how everything comes into play with that particular example. So I apologize. For some reason, my slides are not wanting to advance. Okay, there we go. Okay, so interpreting the slope and intercept. So let's talk about a new example here. Let me just move this out of the way. So let's say that we're interested in trying to predict the price of a set of Legos based on the number of Legos in that set. And if you are not familiar with Legos, they are these little toys where you can build different things with them, little building blocks. So we've gathered lots of sets of Legos, and with each set we've looked at the number of pieces and the price, and this is what we end up seeing. So we have a fairly strong relationship, as you can see. We have pieces along the x-axis, and then we have price along the y-axis. I'm not sure if you can hear this right now, but I'm working from home. I have chickens and they're making noise in the background, so please ignore that. I'll close the window in a little while. But so we're trying to predict price based on number of pieces. And this is what the regression equation looks like. So we can move forward here and put this equation together because obviously we see we have a strong linear relationship. There's something going on between these variables. So it makes sense now to perhaps try to predict the price of a particular set of Legos based on the number of pieces. So again, notice in this equation, we have our predicted price, so price is y, and then we have our intercept and our slope. So what do these numbers mean? How can we interpret these numbers? How can we use these numbers to say something about the relationship? So the actual we're going to talk first about the slope, and then we'll work backward and talk about the intercept. But the actual definition of the slope is that it's the amount that we're predicting y to change as our x variable increases by 1 unit. So in this particular example, how would we interpret that? So we would say, as pieces increases by 1, we predict the price to increase by $0.11. And so again, the slope, the units for the slope would be in whatever the units of measurement are. Here, or whatever the units of measurement for the y variable are. So here we're trying to predict price. So as number of pieces goes up by 1 piece, we're predicting that the price will go up by $0.11. Now, if the slope was negative, we would be predicting that the price would go down by $0.11. So the sign of the slope and the sign of the correlation are going to be the same. If it's a positive correlation, the slope will be positive. If it's a negative correlation, the slope will be negative. Okay, so once we have that, then we can kind of work back and figure out, what does the intercept tell us? There's a couple of different ways we can interpret the intercept. So again, the intercept here is the 2.60. That's one thing that's telling us is where is this line, where's the regression line eventually going to cross over the y-axis? Another way of interpreting it is if x is 0, so if we were to put 0 in here for pieces, this whole thing would drop out because 0 times anything is 0. If x is 0, we would predict the price to be $2.60. So we could write this as if there are 0 pieces, and again, I really apologize for my writing. If there are 0 pieces, we predict price to be $2.60. So again, the intercept would be in the units of what your response variable is. Now, you're probably looking at that and thinking, well, if there are 0 pieces, we don't have a set of Legos, so why would we want to pay anything? Are we just paying for a box? So sometimes, statistically, and this comes up in your textbook, so let me just move this down. Mathematically, we can get a slope and we can get an intercept. And in a second, I'm going to show you the formulas if you had to ever compute those mathematically. So mathematically, we can get these numbers. Mathematically, we can plug things into the formula and we can make predictions. But we have to be careful in terms of thinking about the context of what we're doing. Do those predictions actually make sense? Would it make sense to have x be 0? Sometimes it's not going to make sense given the context of the problem. Here's a case where it doesn't really make sense to have 0 pieces because you wouldn't then even have a set of Legos. So be careful in terms of how you're interpreting these things. Again, there's a mathematic interpretation, but then there's a statistical interpretation within the context of the problem. So if mathematically you had to figure out the intercept or the slope, I just quickly wanted to show you the formulas. So for the slope, you would need to know the correlation. You'd take the correlation, you'd multiply that by the standard deviation of your y variable divided by the standard deviation of the x variable. If you had to figure out the intercept mathematically, it would be the mean of the y variable minus the slope times the mean of the x. So you'd first have to know the slope before you can know what the intercept is going to be. And just notice, we're really probably never going to have you compute these. But I wanted you to see the formulas because, again, I want you to know that the standard deviations of your variables and the means of the variables go into figuring out these things. So if you have any outliers in the data set that are going to affect your means and standard deviations, they are going to have an impact then on your slope and intercept. So it's always important when you're putting that scatter plot together to look for any unusual values that could be having an impact on other things you're going to compute. And then you want to just be cautious in terms of how you interpret what's going on and any predictions you end up making using this equation. Okay, so now that we have a general sense of this, let's just go back to our example with the eyelashes and the eye width. So in this particular example, here's what the regression equation ends up being. And you can see that we have this line. So if we used this equation to make lots and lots of predictions for eyelash lengths anywhere from 0 to maybe about 2, that line is showing us what all those predictions would be. So you can see as you're looking at the line and as you're looking at the actual data values that, you know, if there's some scatter around the line, your prediction is not going to be perfect. So sometimes, for instance, we might overestimate what the actual eye width should be based on eyelash length. Sometimes we might underestimate that. Sometimes we might get it right on. So you'll see there's a couple of points here that are falling right on that line. So the stronger your relationship, the better we're going to be doing in terms of predicting, because the closer those points are going to be to that line. So here, if we had to interpret the slope and the intercept, the slope in this case is 2.16, so that's the value that we multiply by our explanatory variable. The intercept is 0.45. Okay, so the interpretation of the slope. So I might not write this here just because my writing is not good. As I get older, it just gets worse. But I want to say it here for you to write down. So here we would say that as eyelash length increases by 1 centimeter, so remember we were measuring eyelash length in centimeters. As eyelash length increases by 1 centimeter, we predict that eye width will increase by 2.16 centimeters. So since both of these things were measured in centimeters, that's why I'm talking here in terms of centimeters. The intercept. So we could say a couple things. We could say the regression line will eventually cross over the y-axis at 0.45 centimeters, when eye width is 0.45 centimeters. We could say that if eyelash length was 0, we would predict eye width to be 0.45 centimeters. So here it would make sense. You know, you could have a mammal that has no eyelashes, but they still have an eye. They still have a width for their eye. So here's a case where it would make some sense for eyelash length to possibly be 0. So if eyelash length was 0, and again, mathematically, hopefully you're seeing that if this was 0, if we plugged 0 in here, this whole thing would cancel out, and then you would be left with this as your prediction for y. Okay, so I'm going to pause this here, and then we will come back and talk a little bit more about some other things that are coming up in chapter 15.